this session we will discuss about transient response of series RL circuit for DC excitation. In last class we have discussed what is the meaning of transient response and all. So in this circuit now, if you are having R and L and if it is excited by DC source, then what should be the behavior? Here we have R and here we have the inductor L, and if it is excited by the voltage source E, then your circuit, how it behaves, we will see. We'll discuss about this in this session. In series RL circuit, an inductor may be initially charged or uncharged. So here no, whenever switch is open, in that conditions no, sometimes inductor may be charged or it may be uncharged. A driven series RL circuit in which active source is introduced after transition is called driven series RL circuit. If you connect power supply voltage source like this, you can call this one as a driven series RL circuit. In this type of circuit, inductor may be charged or uncharged. Series RL circuit in which an active source is absent. If it is absent, active source is absent, then we will call this one as undriven or source free. If you don't have any active source like this, you can call this one as a source free or undriven. If you have active source like this, you can call this one as a driven circuit. Next, transient response of a driven series RL circuit. We will see about this, how this transient behavior performance do on this circuit. Let us consider that a transition means a change of state from one state to another place. It will take place when you make switch on. In which instant you will make switch on? At time instant t equal to 0, you will make this switch close. In that condition, transient response will take. It is considered that transition take place at instant t equal to 0. At instant t equal to 0, switch will be on. Before transition, before the switch get closes, switch K is kept open. We will keep this switch K open for a long time period. Obviously, if you keep your switch open for a long time period, means whatever the energy that is already stored in past history, that will be dissipated. To find the transient response of a driven series circuit means to find the expression for current through inductor for t equal to t greater than 0. Means whenever you make the switch close, in that condition only you are calculating the current through this circuit. Means when you make switch on, means that is greater than 0. Means at a time instant t equal to 0 will make switch on. So you are finding out of the response whenever t is greater than 0. So it is necessary to have knowledge of initial condition of the current through inductor. You should have the knowledge of initial condition, means before switch get closes, what should be the condition in the inductor, that should be known. You should have knowledge of initial condition, means what energy that is stored in the inductor and capacitor, that should be known. Then only you can able to find out steady state value in the current. Let initial current through inductor is denoted by I naught at a t equal to 0 minus switch K is open. Let us consider that switch K will be open whenever t equal to 0 minus, and we will make switch on at a t equal to 0. So, and before making this switch on, in that condition, let us assume that you have the current I naught in this inductor. You have the current I naught in this inductor before switch get closes. As voltage is not applied to the RL circuit, current in the circuit will be 0. Current in this circuit will be 0. Hence we can write, obviously here before switch get on, before that one you have not applied any voltage source. So because of this they are telling that there is no voltage applied for this circuit. So hence there is no flow of current at all. But here you already told no, you have the current I naught before switch get closed. So what you can see is say what is the value of I naught? It will be 0. Hence we can write, we will see what they have written. Hence we can write current in the circuit or current through inductor is 0 because you have not applied any voltage source for this circuit before switch get turns on at this instant. But we have already discussed that current through inductor cannot change instantaneously, because in previous derivation, in previous concept, we have already discussed that I of 0 minus equal to I of 0 plus, that is equal to 0. I of 0 minus represents before switch on. Current in this circuit is nothing but I of 0 minus. Obviously here in this instant we have seen that before switch get turns on, no? You have not applied any voltage source or current source for this. Obviously there is no flow of current at all in this circuit. Obviously you can consider I naught equal to 0. So I of 0 minus equal to 0. So you can consider I of 0 plus equal to 0. So according to this one they have written I of 0 minus means before switch get turns on. In that condition you don't have any voltage source in this circuit. So I of 0 minus equal to 0, and after you make switch on, in that condition this status is represented by I of 0 plus, and you can represent this value as a 0. So that current is nothing but I naught. For all t greater than or equal to 0 plus, switch K is closed. You will make switch on at instant t equal to 0. So you can say that for t equal to 0 and t greater than or equal to 0 plus, switch K is closed, means you have made switch on. So you can say that voltage source is connected for this circuit. Apply KVL to the circuit where voltage source is now introduced in the circuit. You have introduced the voltage source for the circuit. So we will see that circuit. This is the circuit. If you apply KVL for this circuit, then how we can write this? V equal to minus I into R minus, and then you can write down for the inductor. So they have written minus L into di by dt plus V equal to this. This is the expression by applying KVL for the circuit for the instant t greater than or equal to 0 plus, because you have applied the voltage source V. Whenever switch get turns on, so voltage source V will be introduced in this circuit. So remaining expression is minus Ri minus L into di by dt plus V equal to 0. Simplifying, we will get R into I of t plus L into di by dt. This is equal to V. Then you can rearrange this one and you can write down this expression as, after rearranging in the sense that take this term to V minus R into I, then divide this complete term by R, then you will get this expression. Next you can rearrange this and you will get this di divided by, take this term to LHS side, you will get V by R minus I by T, R by L into D. Integrating both the sides with respect to corresponding variable, then you will get the values like this. If you do integration on both the sides, obviously if you do integration means what? Integration of this term means nothing but ln of V by R into minus I of T. This is equal to integration of constant in nothing but T, you will get this expression. K dash is the arbitrary constant here, you will get this expression. K dash is an arbitrary constant and you will get this expression. To find the K dash. Now what I do, I will find out the variable K dash in this expression. To obtain the value of arbitrary constant K dash, initial condition is used. To find out this K dash, we will use the initial condition. Initial condition is given in the circuit. So initial condition is what? At t equal to 0, means you have done just switch on at instant t equal to 0. In that condition, current will be 0 only. Substituting these values in this above expression, you will get K dash value as what? You have introduced I of t equal to 0. and t equal to 0, you will get this one. You will get k dash value as k dash equal to minus ln v by r. K dash equal to minus ln v by r, you will get this expression. K dash expression you will get like this. Substituting the value of k dash, we get minus ln v by r minus I of t minus r by l of t minus ln of v by r. So here what I did, I have substituted the value of k dash in above expression. Where you have k dash now, substitute that. You will get this one, and you can take this LHS to this side. You will get this term to LHS side. You will get ln of this term minus ln of log of x minus log of y means what is the term? You will get log of x by y. Log of x by y. Log of x minus log of y means log of x by y. This is nothing but this term. This is equal to minus r by l into t. So next what you do, take this logarithm term to this side. It can be represented by e raised to this term if you remove the log on this side. Next, after this one, take v by r to RHS side. This becomes like this. Next, take v by r to RHS side. You will get the expression for I of t. Simplifying for the current through inductor. So this is the current through the inductor. Fine. We will see what are the terms we have in this expression. What is the meaning of this expression? We will see in this next section. In above expression, represent solution of first order non-homogeneous differential equation obtained by applying KVL to the driven series RL circuit. This is the first order non-homogeneous differential equation by applying KVL to this circuit. Above response is a combination of steady state response and a transient response. This is the condition of steady state as well as a transient response. This is the condition for steady state as well as transient response. We will see what is that steady state response as well as transient response we have. So actually in this expression you can observe that you have two terms. One term is steady state, that is the forced response, and next one is the transient response. Forced response or steady state response is denoted by this v by r. This first term, what is this first term? This is the steady state response, that is the forced response. Next term is the transient response. It is due to the forcing function, which is nothing but applied voltage V. This is also called a zero state response. Whatever the V by R term we have considered, that is nothing but forced response. You can call this one as a steady state response. This response is also called as a zero state response. Similarly, transient response is represented by this term. Second term is transient response, V by R into e raised to minus R by L into t, in which time t is involved. So second term represents what? Transient response. This is a natural response of this circuit, which is also called as zero input response, because it is the characteristic of a source free circuit. This is the zero input response. This is the zero input response. It is the characteristic response of source free circuit. Means when you make switch on, now in that condition you can say that voltage is not applied for this circuit. So you can call this one as a zero input response. So here we will get from this expression, it should be clear that I of t equal to V by R minus V by R into e raised to minus R by L into t. First term represents steady state. Second one represents transient response. Transient response decreases with respect to time. second term is called as a zero input response because it is the characteristics of a source free input circuit. So till now whatever the concept we have seen, now we'll go with that one and we'll see once again. So we have considered the circuit. Here you have the switch that is in series with the resistor R and inductor L, and this is connected with the voltage source V, and we will make switch on at a time instant t equal to 0. Before this switch apply, means before this t equal to 0, the time history, that is the past history, can be represented by t equal to 0 minus. In that case you can say that you have not applied any voltage source for this circuit. Let us consider that if your circuit is open for long time duration. Obviously if it is open for long time duration means you don't have any energy in the inductor or capacitor, something like that, it will be dissipated. So, and also in that condition, if you don't apply any voltage source for this circuit for the instant t equal to 0 minus before switch apply, in that condition voltage source V not applied. So in that condition whatever the current that is flowing in the circuit, that current is nothing but I naught. We'll call this current as I naught. The I naught value is 0 because you have not applied any voltage source because switch K is open. So, and also in previous derivations concept we have seen that current through the inductor will not change instantaneously. This is the property of inductor. In previous derivation we have seen that I of 0 minus equal to I of 0 plus, where that is present here you can see. In previous derivations we have seen IL of 0 plus equal to IL of 0 minus, means current through inductor cannot change instantaneously. So because of this, whatever the past history is there, no, that will be continued for some time duration. So I naught will be 0. So we'll write down that expression. I of 0 minus equal to I naught, that is equal to 0. This is equal to I of 0 plus, and after this, for time instant t greater than or equal to 0 plus, you will make switch on. When you make switch on, you will apply voltage for this circuit. Then you can apply KVL for this circuit. For this circuit you can see that for the KVL, minus R into I of t minus L into di by dt plus V equal to 0. For the KVL, this is the circuit. Simplifying this circuit, and you will get, after rearranging and after simplifying, you will get the term like this. Fine. After this one, after simplifying, and if you get the expression for current I of t, this is the final expression. Next, here we have two terms in your final expression. What are the two terms you have? V by R, this is the first term. This is nothing but steady state. Next term is nothing but minus V by R, this one. This is the transient response. First term in the steady state, next term is the transient response of the circuit. Steady state represents this is due to applying voltage. Transient response is nothing but when you don't apply any voltage, whatever the energy that is stored in the inductor, that energy will be decayed. So you can call this one as a zero input response or zero state response because you have not applied any voltage source for this one. Next we'll see how we can able to represent these terms with help of the graph. Show the variation of current I with respect to time. You can see that in y-axis you have represented the current I of t, and in x-axis you have represented the time period t. You can see that as time progresses, whenever t equal to 0, I of t will be 0. As time goes, then current start to increases, means your inductor getting charged. So here you can see that at this time your inductor current will be maximum, that I of t will be maximum, that value is V by R. But at t equal to 0, what is the current value? Current value you can consider I of t equal to 0. As time progresses, this I of t is getting increased. You can see that one through this graph. At instant, at the point P, this V by R will be 0.632, and at this point current I of t reaches to 1. Here 1 represents your current I of t is maximum, and at a point P you can see that your current I of t will be 0.632. Like this you can have different points. While reaching this current I of t from 0 to 1, you can get many of the different intermediate points. So here we will see what they have written. It is clear that the current increases exponentially with respect to time. You have exponential curve. The rising of current produces a rising flux. Rising of current represents rising flux, which induces EMF in the coil. As the current increases, your inductor will be charged, so it introduces the rising flux, induces EMF in the circuit. According to Lenz's law, your inductor opposes variations of current, so you can tell this one in other words as self-induced EMF opposes the flow of current. As this inductor charges, it opposes flow of current through this one. Inductor EMF opposes instantaneous variation of current. Because of this induced EMF and its opposition, current in the coil does not reaches to its maximum value instantaneously. So because of this introduced EMF in the inductor, your current I of t will not increases to maximum value. What is that maximum value? We have considered 1. It will not reaches to maximum value 1 immediately. It will take some time durations to reach this maximum value. The point P shown in the graph denotes that current in the circuit rises to 0.632 times maximum value current in the steady state. Maximum value is 1, but at the point 0.632 it is the maximum value. The time required for the current rise from 0.632, its final value is known as a time constant of the given RL circuit. We will represent the time constant 2. That time constant 2 represents what time it will take in order to reach your current from 0 to maximum. Why it will not reach to maximum value immediately? Because whatever the EMF energy that is stored in the circuit, it will take some time durations to reach from minimum to maximum value. The time constant denoted by 2. Thus, for series RL circuit, time constant 2 is represented by 2 equal to L by R second. To study the significance of time constant, let us substitute different value of time 2. 2 is nothing but this time different time constant t is nothing but 2, 2, 2, 4, 2, 6, 2. Like this. At a t equal to 2, for the first time instant t equal to 2, you can substitute this expression t equal to 2 in above expression, derivation expression. You can substitute t equal to 2 and you can write down that expression. If you substitute that and if you calculate this, you will get 0.632 V by R. Next time instant you can substitute t equal to 2, 2. We will get I of t expression as what? 0.862, 864. Like this, you can observe that at t equal to 2, it is 0.63. At t equal to 2, 2, it is increased. For 4, 2, it is near to 1. For 6, 2, it is near to 1. And here you can see from 2 to 2, 2, it is increased maximum. Maximum value is increased. From this period to this one, increasing value is very less. Like this, now, as charge in the inductor increases to the maximum value, it do maximum opposition for the increasing of current. From above value, from above these values, it is clear that up to first time constant period, initial rate of rise in the current is high. Initial rate means in first instant t equal to 2, rise in the current is very high, but after time constant period this rate slow down. For 4 to 6 to this rate will get decreases for further period of time. Ideally the current reaches steady state value at infinite time, at a t equal to 6 to or for t equal to infinity 2. For infinite time it reaches to 1 value, but practically current reaches to steady state value after 6 to or 8 to. So voltage across the inductor can be represented by VL of t equal to L into di by dt. In this expression, put the value of I of t derivation result what you got. So look at this I of t, what you got, that I of t equal to V by R minus V by R into e raised to minus R by L. And here now you will take that expression V by R, take outside, write down the expression for I of t. So do the differentiation for first term and second term independently, first term and second term differentiation independently. So differentiation of constant is 0, for first term it is 0, for second term V by R is common, differentiation of e raised to minus R by L is nothing but minus R by L into e raised to minus R by t. You will get this expression after rearranging this one, and after simplifying this one you can say this and this get cancels, and this term and this term get cancels. You will get V into e raised to minus R by L. This minus and this minus becomes plus. VL of t equal to V into e raised to minus R by L into t into V. Similarly, for the inductor you can write down VR of t equal to R into I of t, substitute the value of I of t. Then after rearranging you will get the expression for VR of t, means actually here this is the circuit of RL's resistor as well as inductor. For the voltage variation in the inductor we got that previous derivation. For the voltage variation in the resistor you will get this expression. The variation of voltage across resistor and inductor is shown with these two expressions. We can represent these two expressions through this graph. We will see what these graph represents. This curve represents, this is the expression for VR of t. This term represents, this is the expression of voltage across the inductor. So what is the voltage across the resistor take place initially at a time t equal to 0? Voltage across resistor is increasing at a time instant. For particular time instant it reaches to maximum voltage. And also for VL of t you can see that at time instant t equal to 0 it will be 0, but for infinity time VL of t approaches to 0. Whenever voltage reaches to 0, what it represents? You know that V equal to IR. If R equal to 0, then what happens? V equal to also 0. If V equal to 0, what it represents? Your inductor is short circuited. Here at infinity time, inductor will be short circuited. So from this expression we will see what they have written. From the characteristic it is clear that current through inductor increases exponentially. We have seen this is increasing exponentially. Voltage across the resistor also increases exponentially. This is also increasing exponentially. But voltage across inductor decreases exponentially. It is decreasing exponentially for the inductor. It is not increasing, decreasing. When the current reaches to steady state value at infinite time, voltage across the inductor also reaches to steady state value 0, that is 0 value, 0 voltage. Thus in steady state a voltage across inductor is 0. Obviously voltage across inductor will be 0. It acts as a short circuit. If inductor voltage is 0 means what? It was like a short circuit. Let us assume that inductor carries initial current I0 before switching action. Let's consider that if you are having some inductor current I naught before switching action, then you can able to write down the expression for I of t. You can write down the expression for I of t equal to V by R minus V by R minus I naught e raised to minus R by L into t. The variation of current I of t with respect to time is shown in the figure A. So if you are having some current in past history for t equal to 0 minus, if you are having some current, then you can shift this and you can draw the graph from this instant, where current increases from initial current I naught, not from the beginning. It is not from this curve. So I naught is not from this 0 it is increasing, it is increasing from particular instant. Next, VL of t, you can write down this expression VL of t. VL of t is decreasing like this. Variation of I of t and VL of t with the time in series RL circuit with inductor carrying initial current. We'll get this. It is decreasing like this. But VL of t equal to V minus I naught R into this expression. We will get the expression. The variation of VL with respect to time is given by this expression. In above expression, the above response is called a zero state response because it is a response to a non-zero input. Here you don't have any input. This is a non-zero input to a circuit with a zero initial condition. This circuit is called a driven circuit because it is driven by the voltage source V. Here it is driven by whatever the voltage you have, this V. This is the driven circuit. Next, transient response of source free or undriven circuit. Next, in next section we will see about undriven circuit. Here we will consider transient response of source free or undriven series RL circuit. So here in this case, in previous concept we have seen driven series RL circuit. Now we will consider undriven series RL circuit. So in this circuit you can observe that whenever switch position is at A, in that condition inductor will be charged. Whenever it is moved from A to B, then you can say that is undriven because source is source which is connected to this circuit that is moved at the position B. So you can call that one as undriven circuit. You can call that one as a source free circuit. So we will see transient response or source free this circuit operation we will see here. And also here we should observe how the energy dissipated by the inductor when you remove the source, that is V, connected to this circuit. We will see that one. Consider a series RL circuit shown in figure. Consider that initially switch K is at position A. Whenever K is at position A, in that condition inductor will be charged for a very long time before the transition, where switch is at position A for long time duration. This is clearly indicates that network before the transition is initially in steady state. Assume that at t equal to 0, switch K is moved to the position B. Whenever this switch K is moved to the position B at a time instant t equal to 0, we have seen the moving of switch from point A to point B. The analysis of undriven series RL circuit is nothing but finding the expression for current decay in RL circuit. Obviously here at the position A, inductor will be charged. When you move the switch K from A to B, then we can see how the energy stored in the inductor, how it will be decayed. We will study that one here. So we will see at t equal to 0 minus. T equal to 0 minus means it is the instant where you have not changed the switch position from A to B. that is t equal to 0 minus. Switch K is at position P. Initially switch K is at position A. As a network before the transition remains in steady state, inductor act as a short circuit. As a network before the transition, whenever switch moves here, no, it will be in steady state. Inductor act as a short circuit, as we have already seen. Act as a short circuit. Then you can represent that one as IF 0 minus. Before switch on at k equal to 0, for t equal to 0, it is of IF 0 minus, and after switch on IF 0 plus, current IN of t will be V by R. You may be having this much of maximum current you will be having, because current through inductor, and also you can see IF 0 plus equal minus equal to IF 0 plus, because current will not change instantaneously. We have that property. According to this property we have written. Next we will consider the case when you move the switch from A to B. When you move the switch from A to B at the instant t greater than or equal to 0 plus, switch K is moved to the position B from position A. Now the network is without any excitation, because in this circuit you can see that voltage source that is connected in this circuit, that is completely removed. Active source is removed. Hence such a circuit is called source free or undriven circuit. You can call this one as an undriven circuit. Note that now the current will vary from its initial to steady state value exponentially, as immediately after the transition at t equal to 0, means when you have moved the switch from A to B at t equal to 0, steady state condition get distributed and network will try to attain the steady state condition over a period of time. Means whatever the energy stored in the inductor, that try to achieve steady state, means energy inductor try to decrease over a period of time. And also here inductor is not short circuited, because energy in the inductor is get dissipated during this period whenever switch K moves from A to B. So next we will see, we can apply KVL for this circuit. According to energy stored in the inductor try to get discharged, and you don't have any voltage supply for this circuit. You don't have any voltage source for this one. So according to KVL you can write down minus R into I of t minus L into di by dt. You can rearrange this one and you can write down the expression for I of t like this, and you can rearrange this one like this. You can apply ln for this one. You will get ln of I equal to minus R by L into t plus k dash. K dash is the arbitrary constant, and you can find the expression for k dash. K dash will get the expression of for k dash. Using initial condition represents by this equation into this equation. You can substitute using initial condition represented by this equation. What is that equation? You can observe this equation. I of 0 minus equal to I of 0 plus equal to I naught, that is V by R. I will substitute that one here. Next here now we have consider I of t equal to I of naught. At t equal to 0, I of t will be I naught. You can substitute that I of t will be I naught, t will be 0 plus k dash. K dash value we got this one. Substitute the value of k dash in this above expression, and you can write down this expression ln of I naught. Then you can rearrange this one. Take ln I of t minus ln I naught. You can take this one to LHS, and then this is minus R by L of t. You will get the expression ln of I of t by I naught. This is the expression here. So I of t by I naught, you will get this one. Next, take this ones to RHS side. You will get I of t equal to I naught into e raised to minus R by L of t. So I naught is nothing but V by R. You will get I of t equal to V by R into this expression. From this expression it is clear that here you don't have any source. This is a source free, and it is not driven by any voltage source. So you can write down undriven series RL circuit. The current through inductor exponentially decreases. Here you can see e raised to minus R by L. It represents the current through the inductor. decreases exponentially. Here you can see decreasing of the current exponentially. I of t and time period t, I of t time constant. From the graph it is clear that current is exponentially decreasing. At point P, what is that I of t maximum value? That is 0.368. Current value is 0.368 times its maximum value. The characteristic decay of is determined by the value of I and L, which are two parameters of the network. Here you can see that inductor energy not decreased to zero value immediately. It will take particular time duration. This duration is represented by the parameter that is the time constant tau. To study the significance of time constant tau in undriven series RL circuit for a different value of this t, that is t means t equal to 2t, 2t, 4t, 6t, like this. For undriven series RL circuit, you can substitute the value of tau as L by R. Substitute this one in above expression of I of t. In I of t expression, if you substitute this, what is that I of t expression? You can see here. So this I of t expression here, in place of this one, substitute t equal to L by R. Then if you solve this one, for the value of t equal to 2, you will get this. 2 2 you will get this. 4 2 you will get this. 6 2 you will get this. For infinity you will get this. For infinity it represents that your current I of t will be 0, means your inductor is completely discharged. From above expression, above value, it is clear that initially current through the inductor in series RL circuit decreased rapidly to 0.368. It decreased to this value. From this value to this value, it decreased rapidly. Maximum current over first time instant. After this rate of decay slows down, then decaying rate will be decreased here if you compare with all these values. It is observed that current approaches to steady state condition at approximately t equal to 6 to 8 to 2. Next we can write down voltage across the inductor as VL of t equal to L into di by dt, and write down the expression of I of t. I of t expression we already got as I naught into e raised to minus r by L into t. Next, if you rearrange this one, you will get this one. This is the expression for VL of t. VL of t is nothing but voltage across the inductor, that is minus I naught r into e raised to minus r by L. Next, I naught into r is nothing but voltage V, and you can write down that expression by substituting V. Write down that expression. You will get VL of t equal to minus V into e raised to minus r by L into t. This is the voltage across the inductor, which decreases energy in the inductor, decreases with respect to time. Variation of VL of t with respect to time, that is decreasing, that is shown here. Physical interpretation of this result, we must consider that energy in the network before the switch is moved to the position B, energy stored in the inductor is what? 1 by 2 into Li square, as energy dissipated through the resistor is given by I square into R. After switching, when you make switch on, the voltage source is removed and energy stored in the inductor is totally dissipated by the resistor. As time progresses, it start to decrease. Energy is half Li square, start to get decreases at a maximum rate after switching. After switching, it try to get dissipated. The current decreases most rapidly at that time just after the switching. You can see decreasing of the current. This is the concept when you remove voltage source. Here you can observe that circuit with respect to this one. We will see that whenever k equal to 0, inductor will be charged. Whenever you change the switch k from A to B, then you can consider that circuit that you don't have energy source, or that is a undriven. In that condition, whatever the inductor that is stored the charge, it start to get dissipated. Energy in the inductor start to get decreasing. That decreasing is shown with that expressions here. Next we will get all these expressions from these concepts like undriven and driven circuit. We'll solve some problems here. The next concept we'll see the problems. What is that problem? We'll see that. This is the problem. We'll read this problem. What this problem explains. Okay, in this section we will solve the problem related with the RL circuit. Here we have resistor and inductor in the circuit. We will see the problem what they have written. Find IFT for the following network shown in the figure. If switch K is open at t equal to 0. At t equal to 0, so switch K is open at t equal to 0. Before that, circuit has attained steady state. Means before that, this circuit has been charged. They are telling that. So for this one, we have to solve this one. At t equal to 0 minus means before applying the switch, switch K is closed, and you should observe that if switch K is open at t equal to 0 and they are telling that at t equal to 0 minus switch K is closed, they are telling that switch K is closed at 0 minus. Thus R2 gets short circuited. Here you can see that R2 gets short circuited means all the current flow through this switch only. The network is in steady state at t equal to 0 minus, so inductor L acts as in a short circuit. Obviously whenever inductor is not charged at all, it works like a short circuit. Current flow through this inductor whenever switch K is closed, and it will be closed at the time instant t equal to 0 minus. Hence initial condition through the inductor can be given by I of 0 minus equal to I of 0 plus this is equal to I naught. Whenever switch K is closed, what is the current flowing through this inductor? What is the current flowing through this circuit? That is voltage V divided by R1, because inductor L is short circuited. So this is the current expression, I of 0 minus equal to I of 0 plus, because current through inductor cannot change instantaneously. This is the concept. Current through inductor cannot change instantaneously. For all t greater than or equal to 0 plus, K is open. For all t greater than or equal to 0 plus, switch K is opened, means you have opened the switch at t equal to 0, and t less than 0 switch will be closed according to given problem statement. Then you can apply the KVL for this. L into di by dt plus R1 plus R2 into I of t. This is equal to V of t. So here you should observe that you have the voltage source V. If voltage source V is present, then you can say this is a non-homogeneous equation. This is the non-homogeneous equation. Look at the solution of non-homogeneous equation. What is the derivations expression you have for non-homogeneous equation? Just I will move with the derivations result for non-homogeneous equation. For non-homogeneous equation, this is the result. I of t equal to e raised to minus pt integration of q into e raised to pt dt plus k into e raised to minus pt. This is the solution for non-homogeneous equation. And also you should observe that in non-homogeneous equation, your expression should be in this form. These are the standard result. You should remember all these results and all. Whatever they have mentioned in the square box. We will use this one while solving the problem. We will use this one. You can write down this one as, what is that standard expression? I have written that. What is the solution? This is the solution for non-homogeneous equation. And also here you should compare this one with another standard expression, di by dt p into I of t. This is equal to q. So you can observe that this first term represents p, second term represents q. Next, you can rearrange this expression, and you should substitute value of p and q in this above expression. You will get this. And also in this expression, if you consider e raised to this one is a constant, keep it outside, v by l is constant, keep it outside, do the integration, substitute the integration limit as 0 to t, you will get this expression. This is the expression of I of t. And you can see that v into e raised to minus p, this expression is there. And here if you solve this one and if you simplify, this l and this l get cancelled. So this is the remaining portion, plus this one is this one. And also in this expression, if you want to find out k dash, you should substitute the limit. What is that? At a t equal to 0. At t equal to 0, what is the condition? I of t equal to v by r. As just now we have seen, whenever t equal to 0, we have I of t equal to v by r. Next, substitute this t equal to 0 in this above expression. E raised to 0. E raised to 0 is nothing but 1. Next, here also e raised to 0 means what? 1. And here also k into e raised to 0 means what? This is 1. And you will get v by r1 equal to this expression. Next, you will get next you can substitute after simplifying this one, you will get k dash equal to v by r1, because now this term will be 0, 1 minus 1 will be 0, though this term will be 0, then k dash equal to v by r1. Next you can write down the expression for I of t equal to v by r1 plus r2. You can substitute the value of k dash. K dash is v by r1. Wherever you have k dash here, now you can substitute that v by r1. We will get this expression. This is the solution of that problem. We will see another problem related with this. In the circuit shown in the figure, initially switch k is kept open for long time. Long time means t less than 0, it will be open. At a t equal to 0, switch k is closed. Obtain the expression for the circuit for t greater than 0. Find the value of current at a t equal to 0.25 seconds. Find the value of current at a t equal to 0.2 seconds. What will be the current in the circuit in one time constant period? Determine instant of time at which current in the circuit reaches to 1 point. So here we should observe that at a t equal to 0, it will be closed. Whenever t less than 0, it will be open. So first I will consider the case whenever t equal to 0 minus. Switch is open. Switch is open means according to this one, I of 0 minus will be 0, because switch will be open, so inductor is not charged at all. So according to the concept, I of 0 minus equal to I of 0 plus, because current through inductor cannot change instantaneously. Next I will consider for all t greater than or equal to 0 plus, switch k is closed. You have closed this switch k. Next you can apply KVL for this one. You can write down minus 80 into I of t minus 10 into di by dt plus 12, this is equal to 0. Next you can rearrange this one and you can write down this one as di by dt plus 8 into I of t 1.2, and this expression is similar to what this one. Here you can observe that p is minus 0.8 and q is 12. And you write down the standard expression for non-homogeneous solution. Write down this one and substitute the value of p and q. Then you will get this I of t equal to this one. After simplifying this one, you will get this expression. Next, you will get this one, no? And after simplifying this one, for e of e raised to 0 equal to 1, this is the solution. This is a simplified expression here. To find k dash, using initial condition in the equation 3, substituting t equal to 0 and I of t equal to 0, t equal to 0 and I of t equal to 0, because now you have done switch close at a t equal to 0. In that condition, I of t is also 0, because inductor is not charged whenever switch is not closed. So I of t equal to 0, and if you simplify in this one, you will get k dash equal to 0. You should remember this one. In second step, to find out k dash, you were substituting t equal to 0 and k dash equal sorry, I of t equal to 0, we'll get k dash. Then substitute the value of k dash, we'll get substitute the value of k dash in this expression, we'll get I of t equal to this expression. I of t equal to 1.5, 1 minus e raised to minus 0.80 amps. And also you can substitute here. Now we have substitute t equal to 0. Next we will substitute t equal to 0.25 in this expression where you have t. Now substitute this one, we will get I of t equal to this. And next here we have 2 equal to L by R. L is nothing but 10 and 8 is R. We will get 2 as 1.25. Next at a t equal to 2, if you substitute t equal to 2, that is 1.25, you will get 0.9481. And also in the problem they have asked at t equal to 1.2, at a t equal to t dash, if t equal to at some other value t dash, you will get I of t this one. Substitute this one and you will get substitute this I of t equal to, substitute this one in this expression, I of t equal to 1.2 and this is 1.5, 1 minus e raised to minus 0.5 into t dash. Find out the value of t dash. This is the fourth question of the problem we have calculated. At a t equal to 2.01 second, we will get I of t as a 1.2. Its current in the circuit to 1.2 amps. This is the problem. This is how we solve the problem for the circuit which contains RL circuit. Like this you have n number of problems. You can solve like this, you can solve n number of problems. In this case you can draw the circuit diagram also. So these are the concepts for the circuit using RL circuit. We will see what are the university questions you may get. What is time constant? Explain time constant in series RL circuit. Sometimes they may ask the derivations, which one we have done. Like this they may ask the problem related with this one. Just know whatever the problem we have solved, you can see that that type of problem they may ask in the university questions. Till now we have discussed about RL circuit. Next we will go with some other circuits. Thank you.